Hello everybody. Today we will be talking about a special part of the immune system, that is the complement system. Complement system consists of a series of proteins which complement or augment the functions of the antibodies. Again, what are complement system? Complement system consists of complementary proteins. There is a whole multiple series of proteins, the multiple proteins. And what are the functions of these proteins? These proteins basically complement the immune system and complement the inflammatory reactions. Or we can say these proteins augment the immune system work as well as augment the inflammatory response. We will see in this lecture that what are the complement proteins, how they are activated, why they are activated, what are the advantages of activating these proteins, what are the benefits to human beings by activating these proteins, and what are the dysfunctions of these proteins. If these proteins are overactivated, what type of problem they produce to us, or if these proteins are underactivated, what happens to us. First we will talk about the normal function, and then we will talk about the dysfunction of the complement system. Let's start with the normal function. The first question is, where the complement proteins are present and where they are produced in the body, right? Actually, complement proteins are mainly produced by the liver cells. So the source of complement protein in our body is mainly hepatocytes. Liver cells, you know, they produce a lot of proteins. As everyone knows that liver cells synthesize albumin, liver cells, hepatocytes produce many coagulation factors. In the same way, liver cells also produce a series of proteins which are about 20 or more than 20 proteins, and those proteins are called complement protein. Let's suppose this is your circulatory system. Here is your circulatory system. Here is your liver, and liver cells are constantly synthesizing and releasing complement protein in circulation, right? These different complement proteins which are produced, right? Okay. These different complement proteins which are produced in circulatory system, right? There is not one protein, there are about 20 or plus proteins, and these proteins interact with each other. And do you think in a normal person blood who does not have any inflammatory reactions or any immunological reactions going on, do you think in normal person's blood complement proteins are present?
Yes.
What do you think?
Yes, they should.
Yes, they are. Complement proteins are present in your blood all the time. Is that right? Basically, complement proteins are proenzymes. These are inactive proteins. These are inactive enzymes. They are constantly being produced by the liver, added to your blood, right? But they are activated only during the inflammatory reactions and immune-mediated reactions. Is that right? So, major source of complement protein is liver. That is what a good doctor knows. But there are some doctors who are great doctors. They know more than this. That some of the complement proteins are secreted by the macrophages. And another important exception. Complement protein number 1 is mainly produced by the GIT mucosa. That is an exception. Most of the complement proteins are produced by liver. But if you really want to know exceptional things, many of them are also produced by macrophages. And complement protein number 1 is mainly produced by GIT mucosa. Is that right? Anyway, all of them are normally present in your blood. Is that right? Now, let's see how they work, right? We take a practical example that there is a bacteria present in your tissue. Okay, we make one bacteria here. What do you think? It's Coccus or Bacillus?
Bacillus.
Okay, he has high general knowledge. He knows it's Bacillus, not Coccus, right? Cocci are actually circular, spherical, right? So this is one bacteria. And of course, let's suppose this bacteria has these antigens. These are bacterial. These are bacterial antigens. And you know, when immune system is activated, immune system make antibodies against the bacterial antigens. Is that right? let's suppose you have made an antibody against this bacterial antigen, and antibodies are basically, they are two heavy chains antibodies, and they are having two light chains. All these chains are held together by, yes, what are these? Disulfide bonds. Remember the structure of antibody. Antibody is a tetrapeptide. Antibody is a tetrapeptide having two heavy chains and two light chains held together by disulfide bonds. This is the basic structure of the antibody. Let's suppose when this bacteria entered in your body, it activated the humoral immune response, and eventually against these antigens, antibodies are produced. Right? There are many types of antibodies. Right? But antibodies which can specifically activate the complements, they are immunoglobulin belonging to M class, IgM, or immunoglobulins which are IgG. There are 5 main classes of antibodies, right? There is IgM, there is IgG, there is IgA, there is IgE, there is IgD. The complement activating antibody classes are only IgG and IgM. Is that right? Let us suppose that against these bacterial antigens, our immune system has produced IgG or IgM. Any one of these is produced. Once your immune system has produced these antibodies, let's suppose here is your immune system. This is your immune headquarter. Right? You must be knowing that macrophage present the antigen to T helper cells. Macrophage take up the antigen, present to T helper cell, and T helper cell convert the B cells into plasma cells. And these plasma cells secrete the, yes, what is it? Antibodies. Basically this antibody is tetrapeptide, but in a simple way I've shown it like this. Now these antibodies which are produced against this antigen, eventually these antibodies will reach here, and what will happen? These antibodies will, yes, they will react with the antigen. This is an antibody, and now this antibody is reacting with the target antigen. Is that right? When antibody reacts with the antigen, there is a change in this tail of the antibody. It undergoes a change. It is just like that thing that if a boy is standing, there is no change. But if we interact with something, there is a change in voice. In the same way, when antibodies are not with the antigen, they don't have a specific change. But as soon as this antibody molecule reacts with the antigen, there is a change in it. What is the change in it? Let me tell you. Let's suppose this is the Fc portion of the antibody, and Fc portion of the antibody has a special loop here. Right? This point, these 2 points can activate the complement. But normally when antibody is not binding with the antigen, these loops are not available to the complement protein. But as soon as antibody bind with the antigen, these loops become exposed. We say antibody is activated. And here is the answer. You have a lot of antibodies moving in your blood, but they are not activating the complements all the time. Why they are not activating the complements? Because antibodies which are moving in your blood or antibodies which are present in your body fluids, they are without antigens. Until they are without antigens, they are not having the capability to activate the complement system. But as soon as antibody bind with the antigen, it undergoes a transformational change, and it exposes special domains which can bind and activate the complement system. Advantage of this fact is that antibodies will not inappropriately activate the complement system, and antibodies will only activate the complement system when antibodies are sticking with the antigen. That means antibodies will activate the complement system only when there is a need of it. When there is a need of it. Now, as soon as these points are exposed, it means now this antibody which is biting on the antigen, it is activating its tail. It is willing to do some function. Here what is the function? To bind the complement protein and activate. Now of course if there are many bacteria here, there is some injury is going on, it means there is some inflammatory reaction here, and if there is some inflammatory reaction in this area, it means that endothelial cells here are, there is some inflammatory reaction going on, and during the inflammatory reaction blood vessels are dilated, endothelial cells are shrunken, and there is increased permeability. Again listen, because in this area bacterial invasion is there and bacteria are damaging this area, so naturally there will be inflammatory reaction, and due to that inflammatory reaction there will be vasodilatation as well as there will be increased permeability of microcirculation. So there will be more blood coming to this infected area and there will be more proteins leaking out from vascular compartment into interstitial area of this tissue particularly. Because this becomes more permeable, so your sleeping dogs, who are your sleeping dogs? Complement proteins which are sleeping in the blood. Now they have a chance to come here so that they become active dogs. So what happens that from here different complement proteins, they will come out, right? But yet they are not active. These are not active. They're sleeping. Now what happened? Actually, by chance they will start hitting at this point. Whenever complement protein number 1, right, will hit over here, it will be activated. Is that right? Complement protein number 1 has 3 parts. Complement protein number 1 we can show like this, that this is complement protein number 1, right? And this has 3 areas, 3 legs. One leg is called Q, other is called R, third domain is called S. You know ABC, QRS, no need to be upset. And this QRS has nothing to do with the QRS complex of ECG. Is that right? So what happens, we say that complement 1 protein, right, it has 3 peptides or special domains QRS. This Q point can interact with activated antibody in complex with antigen. So what really happens, let's make it and see what really happens, that C1 will bind here, right? And when C1 will bind here, now you will tell me it has opened its eyes. It has become active protein or inactive? It has become active protein, right? And what are these points which are activating here? No, only Q is activating here. This is C1 which is activated. As soon as we come in touch with the antibody which is complexing with antigen, and which antibody? Not every antibody, especially IgG or IgM. Now it become active. When it become active, this is C1 activated, complement number 1. We put a bar. When we put a bar, it means it is active, right? So next time what happens? This is inactive complement protein, and this is active complement protein. So we can put a bar on it. So in the books when you find there is a complement protein written with bar, it means it is which form? Active form. So this is also active form. When it becomes active, it calls some other friends. Come here, there is an antigen antibody activity going, you are needed here. So its friends will come. What will be the next protein coming here? Oh, not directly C3. It comes C4. Right? Now, so second protein which comes over here, right, that binds here and become active. Is that right? Very happy. Because it is being activated by C1. So C1 activates the C4. It activates, this was C1. Okay, I will put it in black color. Or you want which color do we put here? Okay, this is C1. Now what is this? C4. Is that right? Why this protein is called C4? First of all, we should be thankful to the researchers that there are many complement protein, and we should be thankful and obliged to those researchers who did not put their names on these proteins. They just call it protein number 1, 2, 3, 4. And these numbers are assigned according to the sequence in which these proteins were discovered. So unfortunately, protein number 4 was discovered before the 2 and 3. So that is why it looks a bit out of order. Is that right? But this was the order in which they were discovered. Right. So complement 4 is activated by C1. Right. Once it is activated, normally, now I have to make another diagram here. Let's suppose this is an inactive complement protein. It's just like a baby. And normally it has a very special domain, and it is like a, what is it? It looks like, you have seen? It's apple, sure. So you can say this protein has two parts, a baby part and baby with apple. This complement protein has two parts, baby part, apple part. Or we can simply say baby for B for baby and A for apple. So it's B part and this is A part. So most of the complement proteins have A for apple, B for baby. No difficult to remember. This A and B, when they are complex together, they are inactive. When they are stimulated, look, baby is sitting like this with an apple on its head, and it is activated, what will happen to apple? It will go away. So what we will say, that when it is activated, right, baby become active, right, but apple has gone away. What is left behind is, for example, complement, which fragment? Baby fragment, B fragment. And which fragment has gone away? Complement, A fragment. Is that right? So many of the complement, right, they consist of a complete protein, and when that protein is activated, some of the complement break down to two components. One component is called B component, other component is called A component. Is that right? Am I clear? B for baby, A for apple. But here B is not for baby. Here B is for the fragment which remain binding with the original complex. One fragment fall away, other remain bound. B for binding. Let's see what happened. This was C4. When C4 is activated, which component is lost? Yes, please. Right? So what will be this? C4A. And what will be this? C4B. So what we can say? That when complement number 1 is activated by the antibody, Fc portion of the antibody or tail of the antibody activate complement number 1, complement 1 protein activates the complement number 4, and complement number 4 hydrolyzes or breaks down into two components. One remain bound with this. This is called fragment B. One fragment diffuses away into fluid form, and that is called fragment A. So apple goes away, baby stays there. Am I clear? Now, once this baby C4B is there, it will attract another baby. And what is that baby? That also become active. And that is C2. And which fragment remain behind? B fragment. And which fragment will go away? Another apple will go away. This apple was from here. Another apple is from here. What is this? C2A. Yes.
I have a question. Did C1 also have complement A?
Of course not, as we can see there.
It just started.
Yeah, it never had apple. It never had apple, it's not going to lose it. So her question was that, will C1 break into A and B fragments? Answer is no. C1 just touch the active antigen antibody complex and becomes activated. And once it is activated, it produces the hydrolysis of C4 and then C2. So C4 break down to A and B component, B remain bound, A diffuses away. A diffuses away, A from away, going away, right? Then C4B will activate C2B. And when both of them are activated, C2 will break down also into A for away, A for apple, A for away, and C2B will be bound. Is that right? Any question here? Now, these two baby become naughty. They become active. They're very happy. You know, one baby is okay, but if two babies are together, mothers know what will happen. This complex is very active. They plan to activate one more molecule, which is the real central molecule of complement system. That is C3. Now there's a turn for the C3. So another baby is coming there, and this baby will be activated by the C3, and it will also lose its apple. What will be that? C3A, right? And what will be left behind? C3B. So it means that this complex which is C4B plus C2B, this complex was able to convert the inactive C3 into active C3. Am I clear? These two babies were able to activate the next baby. So we can say the B fragment of 4 and B fragment of 2 together make a complex which can convert the C3 protein, complement number 3 protein, into B fragment and A fragment. It means they can convert, these two can convert C3 from inactive form to active form. That is why these two baby group is called, another name for, special name for this is C3 convertase. What is it called? C3 convertase. These two are called C3 convertase, which can convert the complement number 3 into active form. Okay, someone find the mistake in my spellings. I'm always weak in spelling, so I prefer to write it like this, that it is C3 convertase. Is that right? Now you are happy. Fine. So this is C3 convertase, these two. Now, how many baby together? This was 1. How many B component? C4B, C2B, and now one B more is added. What is that? C3B. Now look, these three are more naughty. Now they become all of them together. You get it? All of them now, there is not the problem produced by two babies. How many babies? 3 babies. Right? And this is baby business. They will activate one more baby. How many babies have gone? 1, 2, 3, 4. What is left now? 5, of course. Usually 5 is after the 4, isn't it? So 5. Now, which protein will come into action? Complement number 5. So, all these 3 together now activate, wake up the protein number 5. Please be active. There is something bacteria here, right? And now, right? C5, and it will of course lose its apple. So what is lost? It will lose one fragment, C5A, and what is left behind? C5B. Is that right? It means that all 3 of them, all the red complex, which consists of C4B, C2B, C3B, all of them were able to activate which protein? So what should be that complex called? C5 convertase. You are yourself intelligent, isn't it? People have friends which are intelligent. C5 convertase. So now we know, again, let's repeat up to now, how the complement system is being activated under these examples. Right? That there were bacteria here, and these bacteria have been in our body for significant time, so that this bacterium has activated the immune system. An immune system has provided the antibodies against this bacterial antigen. If these antibodies belongs to IgG group or IgM group, as soon as this antibody will complex with the antigen, especially if IgM as a singlet or IgG as a doublet, single molecule of IgM or double molecule of IgG, G, especially IgG 1, 2 and 3. IgG has 4 subclasses. So 1, 2 and 3, they can activate the complement. IgG subclass 4 cannot. But anyway, if IgG or IgM bind over here, the tail portion of the antibody, which is called Fc portion of the antibody, it undergoes transformational change. And during this, the molecule exposes the active part, which is able to interact with C1. As soon as C1 interacts with the antigen antibody complex, C1 becomes active, but it does not fragment. C1 does not break down into A and B. C1 is not a baby, right? And it does not have an apple. Okay, let's change its face so that you remember it is not a baby. It is not a baby, right? So don't talk about C1 B component or A component. Is that right? So this is for C1 is the mother. As soon as mother is activated by antigen antibody complexes, C1, babies will be activated in series. It's too logical to understand, right? Baby number 4 is activated first. Then it activates the baby number 2. So in this way, their apples are lost. So what we can say that C4 break down into A and B component, B remain bound with the initial complex and A component, apple components go away. Then C2 also break down into A and B, A moves away, B remain there. When C4B and C2B make a complex, they convert into a special proteolytic enzyme complex which is called C3 convertase, which can convert the C3, called the baby number 3, and activate that. Of course, any baby who has lost an apple will be very active and weeping and crying and disturbing, right? So C3b will be there, right? So the first two, these two together act as C3 convertase, right? As soon as C3b fragment is added to C3 convertase, whole complex is called C5 convertase. That is C4b, C2b, C3b. This C5 convertase will activate protein number 5, and protein number 5 will break down into C5a and C5b, and now C5b will be sticking to this. Is that right? C5b remain sticking to this main complex. In this example, suppose, now what happens? Yes, what happens now? Actually, now this whole complex can do a very, very dangerous thing to bacterium. Don't forget bacterium. All these babies and their friends are coming to destroy the bacteria. They're not just playing a game for you. They're going to destroy bacteria. And now the real action will start. C5b opens a special pocket here. And who binds here? Yes. C6 and C7. And then with them who binds? C8 and then C9. You know the counting, isn't it? So C5b will activate C6, 7, 8, 9. All this complex, now it is very important to understand, whole this complex, right? This complex, what is that? C5, B, C6, C7. First of all, these two bind with C5, and then what bind? C8 and C9. Let me tell you what are these proteins. Actually, these are special type of proteins which have a shape like this. These are peptide molecules. These are special type of peptide molecule. These are very, very dangerous. You know, they're making a unity and then they become fight against it. All of them will make a circle. How they will make a circle? Look at it. This was C5b. On the flanks of it will become, C6 and C7. Then what will be added to further? C7 and C. So okay, C8 and C9. And all of them will come. They are laughing. They have made a friendly circle, which is least friendly to the bacterium. They are only friendly with each other. They will make a circle like this. So it means this protein, this is making a sort of complex which is having a pore in the center. Is that right? This complex can be also shown like this. They have assembled into a, what is this? Now let's suppose C5B. This is the peptide C5B. Width on the flanks, what are there? C6. And what was here? C7. C6 and 7. And what were here? Yeah, C8 and 9. All these proteins assemble together and make a special type of membrane protein complex which have a central pore. And this will simply detach from here and fall on the bacterial surface. And when it will fall on the bacterial surface, what do you think? If on a simple membrane we put a very strong acid, what will happen to that? It will produce a hole. In the same way, this will fall on that and it will dissolve here like this. These protein complex, so repeatedly more and more complexes will fall. So do you think membrane is under attack or not? It is just like you are drilling holes in the membrane of the bacterium. Do you think bacteria will be very happy with this thing? It is just like putting a drill machine, grrr, grrr, grrr. Will you survive longer? Same is true about bacteria. These biological molecules which are generated by activation of complement, especially C5b, 6, 7, 8, 9, these are very naughty, they circularize and then attack the membrane. So this naughty group of activated complements are called membrane attack complex. So the whole purpose of all this activation was to produce membrane attacks complexes. And these events, before that, these events are called early events or early steps in complement activation. And these are called terminal events or late events in activation of complement. Is that right? The purpose of whole this game was that we could produce membrane attack complex. What is membrane attack complex? This consists of the last components of the complement activation system. C5b, 6, 7, 8, 9. And they make pores. And they don't digest the membrane enzymatically. No. They don't do enzymatic damage to the membrane. They simply these circularize and mechanically they dissolve into lipid membrane of the bacteria and then they produce, this disrupt the physical integrity of the bacterial membrane. These membrane attack complexes disrupt the physical integrity of the bacterial membrane. So of course, can bacteria keep its private environment in? No. The things which are inside will leak out and unwanted things will move in. So bacteria will die. Is it difficult to understand? This type of attack is, do you think, more effective on gram-positive bacteria or gram-negative bacteria? Gram-negative bacteria has outer lipid membrane. Gram-positive bacteria do not have outer lipid membrane. Let me tell you a little thing about gram-positive bacteria and gram-negative. What is the real difference? Gram-positive bacteria has lipid membrane in which it is cell membrane of the gram-positive. Here is cell membrane of gram-negative. These two things are common. Then gram-positive has lot of peptido. What is this? Glycans. These are special type of molecules. They make a very thick layer, peptide molecule cross-linked by glycan units. So this is gram-positive. Gram-negative has a very thin peptidoglycan, and for their special function, they are having outer additional lipid membrane. This is gram-negative. This is gram negative, and here it is gram positive bacterium. What do you think? Membrane attack complex will more effectively attack the gram positive membrane or gram negative membrane? Where membrane is more accessible? Look, if I keep my hand too much exposed, chances of being attacked are more. The best way to confirm is walk on the road, very busy road like this. Is that right? Is that right? But if you keep it like this, less chances to be attacked. Gram positive has membrane only inside. Gram negative has a membrane outside as well. So, membrane attack complex can more effectively destroy gram negative bacteria and less effectively going and destroying gram positive. Now you may be thinking, why am I highlighting this thing? Because in some inherited disorders, you don't have these proteins. And the people who do not have enough complement proteins which play a role in the last part of the complement system. For example, if Mr. Abdul does not have C5b or 6, 7, 8, 9 or any one of them is deficient, especially C6, 7, 8, 9, we call them terminal components of the complement system. If he has deficiency of this, problem will be mainly with gram positive or gram negative handling. Gram negative. So gram negative bacteria will attack him more. So Mr. Abdul will suffer especially with some special bacteria. Right? For example, Mr. Abdul and Mr. Ehsan, they are having the same activities and both are getting the gram negative bacteria, but Mr. Abdul has less these components, so he will suffer with gram negative bacteria more. Who will suffer? Abdul or Ehsan? Abdul. And you know which special type of gram negative? You really want to know? There's a very special type of gram negative which specially attack those people very severely who do not have these components. We don't know why especially those gram negative are too much active in these people. You can guess about Mr. Abdul. Even though the activities of Abdul and activity of Ehsan are same, but same bacteria are being exposed to both of them. But he has more chances to suffer with recurrent infections of those bacteria, right? Abdul has more chances because he has less these components and he has less chances. Of course, bacteria are gram negative, but a very special group of gram negative. You know gonorrhea, gonococci. You don't know gonococci? You know gonorrhea infection, sexually transmitted bacteria, gonorrhea or gonorrhea, whatever you call it. But these gonococci or gonococci, whatever you love to call them, right? And plus meningococci. Gonococcal infections and meningococcal infections are especially more severe and more recurrent in the patient who have deficiency of terminal components. Is that right? Am I clear to you? Right? So gonococci and meningococci as a group are called Neisseria. They are called Neisseria. The spellings are like this. Neisseria group of bacteria. Some people write, I suppose it is right, but anyway you understand even if it's not right. Is that right? So next time if your MCQ it appears a person is repeatedly experiencing the Neisseria infections or gonococcal infections, what's wrong with him? Of course, one reason may be that he's having too much sexual activity in a very much reckless fashion, but other reason may be that he's having these also deficient.
What's the name of the disease? No, the deficiency of the common.
We don't, thank God, no doctor put a special name to the disease of this condition. They just say the people who have deficiency of terminal components of the complement protein, they are more vulnerable to the gram-negative bacterial infection, more specifically about Neisseria bacteria. Of course, there are two groups, gonorrhea and gonococci and meningococci. Is that right? Am I clear? But gram-positive bacteria, they handle well. You want to know why? It means killing in gram-positive bacteria through the complement system may not be requiring this thing, even remaining this component up to this can manage the gram-positive. Should I tell you how? Okay. Actually, there's one more function of complement system. Up to now I just told you that complement system in this given example has produced membrane attack complex and damaged the physical integrity of bacterial lipid membranes. Am I clear? But it's not necessary you drill holes into your enemy. Do you think if you tie your enemy with the lion, and lion will eat up the enemy? This is one more way how complement work. Let me tell you how. Let's suppose this is a gram-positive bacteria. Of course, it must be weeping, isn't it? Why? Why? Because complements have attacked. Why? Because antibody bind here. This bacteria is attacked, marked by the antibody. Antibody tail become active. Now you will tell me who will bind here? C1, and that will activate which one? C4, and what will remain there? C4b, and what will go away? C4a, and then what will bind here? C2b, and what will go away? Another apple, which is C2a. Is that right? And these two are called C3 convertase. So they will activate what? Yeah, C3b, and what another apple will go away. What is that? C3a. Right? Now you can say this bacteria is hooked with C1. Actually, bacteria was chained by the antibody. Tail of the antibody activated C1. C1 bound C4b and 2b, which activated C3b. So all these are sticking to what? Bacteria. Is that right? Now, what happens? That all of them are sticking together on the surface of bacteria. Am I clear? Is that clear? No problem? Now, who are the dangerous lions which eat up the bacteria? Neutrophil then macrophages. Neutrophil then macrophages. They love to eat up bacteria. They eat up the particulate matter, particles. Look, imagine here is a neutrophil or macrophage, and it is trying to eat this bacteria. Whenever it tries to eat bacteria, bacteria may slip out of its mouth. Is that right? But in it, it has a special pocket with which it can bind with C3b. But there is no complement bind with it. But look at another bacteria. This is a bacteria. This is a bacteria with C1, 4b, 2b, C3b. So C3b is there. Now, okay, A components will go away. Who is here? Macrophage. Actually, this portion of this is a special protein which is expressed on the neutrophil and macrophages, and this protein loves to stick with C3b. You get it? So if any bacteria is unfortunately having C3b attached with it, and this touch any neutrophil or macrophage, can this run away? It cannot run away. It's just like that I tie you with a very big dog with a chain. Chain consists of especially C3b. And now can you run away? Dog is there with you, isn't it? This is a special function of C3b. The C3b has receptors on the neutrophil and macrophage membranes, and whenever neutrophil or macrophage find a bacteria attached with C3b, right? So C3b will activate the receptor. This is called C3b receptor. This gives very powerful signal, gives a very, very happy signal to the macrophage internal side. Congratulations, we have a bacteria which is loaded with C3b, it will never go away, let's grab it. Super opportunity. I say simply, C3b enhances the phagocytosis. Bacteria can be phagocytosed without C3b, but slowly. If there are 10 bacteria here, without C3b, they will be phagocytosed slowly. But if there are 10 more bacteria, and on their surface, what is this? C3b molecules. C3b on one side are holding with the sticking to bacteria, other side they can stick with the neutrophil or macrophage. It is just like bacteria now find, neutrophil or macrophage now find bacteria which are having the jam on it, and they will be eaten up very deliciously. Are you understanding it?
Yes.
Am I clear? So we can say C3b facilitate the phagocytosis of bacteria. Is that right? Any molecule which facilitate the phagocytic process is called opsonin. What is the definition of opsonin? Opsonins are those molecules which on one side can bind with bacteria, on other side can bind with neutrophil or macrophages and hold the bacteria and neutrophil or macrophage together, and they facilitate the process of phagocytosis. So it means opsonin molecules amplify the phagocytic process. One of the opsonin molecules you right now know is C3b. There's one more you are supposed to know. Excellent, IgG. One of the antibody, look here. Now I will tell you something interesting. Let's suppose this is a very happy bacteria. Why? Because it does not have opsonin attached with it. If neutrophil try to eat it, it may fool that. Is that right? And neutrophil is really worried what is happening to it and having lot of sweat to eat it. Right? Very sad neutrophil. Having tears. Opposite to that, here are two neutrophils which are very, very happy. Is that right? There is one neutrophil here and there is one more neutrophil here. Very, very happy. You know why they are happy? Because this bacteria is very sad. And why this bacteria is very sad? Because it has sticking to it C3b. On one side it stick to bacteria, on other side it's sticking to the neutrophil. So it will be sure eaten up. Another is that another bacteria which does not have C3b but still very sad. Right? Why? Because it has antibody, especially IgG. IgG on one side bind with the bacteria, other side its tail become active as soon as it bind with the antibody. Either it will activate the complement system or it may interact directly with the receptor of neutrophil or macrophage. And this receptor is for which one? Which molecule? Fc portion of IgG. So it means neutrophil and macrophage have receptor for, neutrophil or macrophage have receptor for C3b receptor, as well as they have receptors for on their surface, Fc portion of IgG. Right? So any bacteria which is coated with C3b will be caught very effectively, or any bacteria which is coated with IgG will be caught by these neutrophil or macrophage very effectively. It is not only true about bacteria. Even if your RBCs are coated with IgG, they will be very rapidly phagocytosed by macrophages. If your RBCs are coated with IgG molecule, they will be very rapidly phagocytosed by macrophages, and excessive breakdown of RBCs will be pathological hemolysis. Is that right? So if you produce autoantibodies IgG against your own RBC proteins, your RBCs will be very rapidly phagocytosed and you will develop hemolytic anemia due to hemolysis, breakdown of the RBCs. Am I clear? So now we can define opsonization. What is opsonization? Opsonization is the process in which opsonin molecule bind on one side to the particulate matter, which may be a bacteria, which may be a tumor cell, or which may be our own cell like RBC. Opsonin molecule on one side bind with particulate matter, and on other side they bind with the receptors on phagocytic cells. And opsonin molecules enhance the phagocytosis of particulate matter. You must know two opsonin molecules, especially C3b and IgG. Am I clear? Now, let's see a very interesting thing. How antibodies can kill bacteria. How antibodies can kill bacteria? There are so many ways. You know, if wife wants to shout on the husband, she can shout in how many ways? Only husband knows, so many ways. In the same way, when antibodies are going to damage the bacteria, they have so many ways to do it, not only one way. Look, this is a bacteria, this is another bacteria. We'll look at only three ways. What are here? What is this? Yeah, antibodies. Here this antibody wanted in a simple way destroy the bacteria. It never activated the complement. It didn't take help of other community people. Antibodies stick with this and just activated the receptor on macrophage. And this bacteria will be very rapidly phagocytosed, and that process will be called direct opsonization, because complements are not involved. Antibody led to the direct opsonization of the bacteria. Is that right? Am I clear? Now, sometimes antibody like to play. How antibody likes to play? This antibody activate complement with it. So it will activate C1, right? Then C2b, C4b, yes. Then 2b, then C3b. Now antibody has partially activated the complement. Then this C3b will stick to the receptor on I think it's not a very decent way to kill the bacteria. The antibody little bit played, activated little bit a series of complement system up to C3b, and then C3b stick to and specially activate the phagocytic cell. Please pick it up. Here antibody directly doing, here it is indirectly doing. This is also opsonization. This is also opsonization. This is opsonization by IgG. This is opsonization by C3b. We say this is direct opsonization and this is indirect opsonization. Am I really clear? Hans? Understanding it? I'm so impressed, but not surprised. I know you understand sometimes. Now, sometimes antibody say, okay, I don't want to take the help of, antibody decide that it does not want to take help of neutrophils, right? It just want to take the help of complement. Antibody binds with the bacteria, and it is a very cruel way to kill. Now it will activate C1, 4b, 2b, both of them act as C3 convertase. Then they activate, it was here C3b. So what is this here? 3b. And then activate, yeah, C, 5b, 6, 7, 8, 9, and all of them make a membrane attack complex, and this antibody keep on moving its tail, and this series remain active and keep on producing these terminal membrane attack complex. One membrane attack complex fall down, another C5 come, and again another attack complex form, so multiple holes are produced, right? It must be also very, very sad. Now you see how antibodies can kill bacteria. They can kill bacteria by direct opsonization. They can kill bacteria by indirect opsonization, or they can kill bacteria by activating the complements up to the terminal level until they produce multiple membrane attack complex and produce multiple holes. Am I clear?